Hi and welcome to Unit 1 Topic 1 Video 6 where we're looking at permutations with restrictions, and it's going to be a bit of a continuation from our last video where we look at the same example but consider what happens if there are some restrictions. So let's consider example 3. In example 3 we said how many ways can a 4-letter word be made from the letters in the word history. So history has 7 letters, and you recall that the answer to this question was 840. 4-letter words from history, which was made up in our previous video of 7 ways of choosing the first, 6 ways of choosing the second, 5 ways of choosing the third, and 4 ways of choosing the fourth. Multiplied together gives us 840. But our next question is, what if the letters S and T have to remain together? So for this question, we consider there's a couple of little ambiguities in the question, but let's look at the simple case. Let's imagine now that the letters are actually H, I, and then ST, because they have to remain together, O, R, and Y. And so now, mathematically, we've kind of got 6 objects, not 7. So from our 6 objects, we can now select our 4-letter word. But keep in mind, it's a 4-letter word. So we've got a bit of an issue, because if we choose a 4-letter word with STN, we only need 2 other objects. But if we choose a 4-letter word without STN, well then we need 4 objects, not 3. So the ST being a double word creates a case-by-case situation which we have to consider. So let's consider first of all case 1, and that case, case 1, that case is where ST is in the word. So if ST is in the word, it means that we have ST and then 2 other objects. So this will be 5 remaining objects, not including ST, H, I, O, R, and Y. 5P2, we're choosing 2 out of the 5. And then we have to multiply this by 3. So this is a little bit more technical in terms of counting techniques, but the reason being that ST is definitely in, but ST could go in position 1, or it could go in position 2, or it could go in position 3. And the order of the other 2 objects is already accounted for in the 5P2. So this is for ST being in. 5P2 is equal to 5 factorial over 3 factorial, 5 minus 2, times by 3. And this is equal to 5 times 4 times 3. Of course, you'd have a calculator as well. 5 times 4 times 3 is 60. And then we have case 2, which we'll do on the side here. And case 2 is ST is not in. So no ST. Which means that now we have to choose 4 separate letters from the 5 that remain. So this is 5P4, and we don't have to worry about the multiplying by anything like 3, because the ordering is already taken accounted for in the P notation. So 5P4 is equal to 5 factorial over 5 minus 4 factorial, which is 1 factorial. It's 5 factorial over 1, 5 times 4 times 3 times 2, which is 120. And so in total, there are 180 different ways of choosing a word that has S and T together. But there is kind of a second part here, because what if they had to stay together, but in any order? And it wasn't implied that they had to be ST in that order in the first part of the question. If we say in any order, which is the other case that might be true here, well, it's pretty easy, in that we consider our case 1 was ST is in, and there are 60 ways, but we have to add to that another 60 for the TS options where they're reversed. And then case 2, of course, was no ST, which was 120 ways, and because ST is not included, we don't need to double count the ST because we don't need to think about TS. They're not included, therefore they're not counted at all, and that gives us 240 possible options. So I've just swapped that out. 240 possible options where ST or TS are together. So just take a moment to have to think about how that works. Because it's a bit more complex, and because we're talking about 4-letter words, not specifically 4 objects, we had to consider a case-by-case basis, and it's always worth breaking down the more complex ones in the case-by-case where required. So the types of restrictions that you might see, and we'll do another example before we finish this video, are things must be kept together, or maybe things must be kept apart. And I'm going to do this example in a second, but things must be kept apart is really tough. The easiest way to do a things must be kept apart is to consider, well, how many ways are there of keeping them together, and how many ways are there where we don't care about whether they're kept together or apart, and then do a subtraction. So I'll show you this in example 4. The other type of restriction is a restriction applied to position. So for example, if a word has to begin with a vowel, or maybe you're making a number out of a random selection from the single digit numbers, but of course 0 can't be at the front because that wouldn't make it a 3 or 4 digit number or whatever the restriction is. So let's have a look at example 4. A group of 4 adults, 3 girls and 2 boys are to be sat in a particular order at a cricket match. How many ways can this happen if the 2 boys must sit together? What if the 2 boys must sit apart? So let's consider this as a part A, part B question. And in part A, the 2 boys must sit together means that we're going to deal with this as currently there's 9 people going, we're going to deal with it as an 8 object situation. So we've got adult, 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 girl, 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 and then the 2 boys are going to be sitting together. So that's the situation there. And to calculate this, we're going to have to start thinking about some technicalities in terms of possibly considering cases or considering how this might actually work. So the first thing we're going to consider is there a distinct difference between people? So is each adult different to each other? Because it's not just the letters in a word anymore, where an A and an A are the same. 2 adults we think we should be able to agree is considered 2 different people. So we're going to treat it like 2 different people, which means that each of these objects are unique. It also means that we've got boy 1 and boy 2, and this could also be boy 2, boy 1, and that is a different ordering. So we also have adult 1, 2, 3, and 4 to consider, and girl 1, 2, 3. So always take a second within a context in particular to think, are these distinct objects or are they different? And in this case, they're distinct objects. So we have to treat them as 9 different distinct objects. So that means that we're choosing an order for 8 people out of a group of 8, which means that we have 8P8. But we also have the boys could be reversed. So we have to multiply by this by 2, or 2P2. And so 8P8 is equal to 8 factorial over 0 factorial times 2, which is just straight up 8 factorial. 0 factorial is 1, and 8 factorial is 40,320, times by 2 is 80,640. It's a lot of ways. So there is 80,640 ways you could order this group of 9 people, such that the boys are sat together. Now, part B, we want to calculate, well, how many ways could we have the boys sitting apart? And so if we say that this is the number of ways that we could have 9 people ordered, which is, of course, 9P9, and then this is the number of ways that we could have the boys together, then the remaining bit on the outside is the number of ways of having the boys apart, because the boys are either together or apart. So they're called complementary events. They give the total number, the total possible number of outcomes. So you can always solve a problem by considering, well, if I can't solve the actual problem, can I work out all the not parts? So the not boys sitting together, or the not boys sitting apart, which in this case would be boys sitting together, and we've done that in part A. So I'm going to do 9P9, the total number of options, minus the answer to part A, which was 8P8 times 2. And 9P9, we should get something that's quite big here for that subtraction, is 362,880 minus 8P8 times 2, which we already worked out as 80,640, and that gives us 282,240. That should have a 0 on the end. And of course, this is an answer that we're happy with, because we expect if you randomly mix this group of 9 people up, there's more chance that the boys are sitting apart than together. So there's example 4, part A and part B. That part B is a pretty common type of question, and in particular could come up as like a complex familiar question where part A is not asked of you. So you need to do that analysis yourself and work out how you're going to go about it, and you really have to calculate part A as well. So there we have the end of video 6, a couple of examples of permutations with restrictions. All the best.